Everybody, welcome back to another video from your favorite calculus teacher, Mr. Molikash. I'm going to start transitioning now from the differential part of calculus to the integral part of calculus. If you remember my very first video where we started talking about what calculus is and an introduction to limits, we'll talk about that in a moment. Now, this next part, for my students especially, just to piggyback off of my last video on L'Hopital's rule, so just to kind of say a way of saying goodbye to derivatives is to do a final derivative question. Let's say that we wanted to evaluate the limit of an expression, right? The limit as x, how about x approaches infinity? The limit as x approaches infinity of, I don't know, x squared plus 1 over x plus 1. Now, if you do what's called direct substitution, this does not equal infinity over infinity, but the top gets infinitely large and the bottom gets infinitely large. And remember what we used to do in problems like this, you certainly can't make it equal infinity. That's not, it doesn't equal infinity. The limit approaches infinity, but what we used to do was we would take each one of these terms, and I'm trying to get my pencil to work here. Alright, so this would equal the limit as x approaches infinity, and we would take the largest power in the denominator, which is x to the 1, and we divide every single term by x to the 1, right? So you divide this by x to the 1, 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 and then what happens is, this becomes 1, right? And then you have the limit as x approaches infinity of 1 over x, because you can move the limit inside the expression, right? This turns out to be x, so we're going to take the limit as x approaches infinity of x, and then over here, same limit as the bottom. And then you evaluate all these limits separately, right? The limit as x approaches infinity is just approaching infinity, right? And then up here, the limit as x approaches infinity is 0, and down here we have 1 plus 0. So this does not, this limit equals these limits, but infinity is not a number, so we say that the limit approaches infinity. Okay, we don't say it equals infinity, although some textbooks do use that equals to mean approaches. But this is the way we used to do it, right? So what if we did away with all this and we used L'Hopital's rule from last week? And we can use L'Hopital's rule because the form infinity divided by infinity is in an indeterminate form. So, remember, if you try to substitute your value or even an infinite value, and you get infinity over infinity, this is an indeterminate form, right? The most common one is 0 over 0, but okay, so what we can do is we can evaluate this limit by using L'Hopital's rule and take the limit as x approaches infinity of the numerator's derivative separate from the denominator's derivative. And then this obviously is infinity because you get infinity divided by 1. The same thing you did before, but it takes a whole lot less work, doesn't it? And so you just have to make sure that your form is an indeterminate form. You don't want to use L'Hopital's rule on forms that are not indeterminate. For example, let's say that you want to do the limit as x approaches 2 of x squared minus 4 over x minus 2. If you try to do direct substitution, you get 0 over 0, and you're cool for L'Hopital's rule. L'Hopital's rule, right? But if you did the limit as x approaches 3 of this same expression, we would not use L'Hopital's rule because we can directly substitute 3 in, and we get 5 over 1, which is 5, right? So no need for L'Hopital's rule. In fact, if you did L'Hopital's rule, you'd get the wrong answer, right? On top you'd get 2x, on the bottom you'd get 1, and you would think that that would be 6. Whoops, no bueno, it is not 6, it is actually 5. Okay, so you do not want to use L'Hopital's rule unless direct substitution gives you an indeterminate form. And I did want to just share that with you and remind you that infinity over infinity is another indeterminate form. Okay. So off we go into the beyond past derivatives. So if you remember my very first video, I started talking about, the first part of the class was going to be limits, and we did a lot with limits. We evaluated limits using a table of values, using algebraic techniques, using graphs. And then we did a couple of chapters of derivatives and the applications of derivatives. So you found derivatives using the product rule, quotient rule, chain rule, power rule. And you applied derivatives, not just in L'Hopital's rule, but how to find relative extrema, how to find absolute extrema on a closed interval. Related rates was another application of derivatives. So now we're moving beyond derivatives into something called integrals, and it's going to take us a couple of weeks to kind of get into that, right? And another thing I would like to tell you is that this thing that we call an integral, it looks like an S, and it, just to remind you from our first video, which is way back on August 16th, right? That the integral is related to a sum. It's actually the limit of a sum, and it's the sum of products. So the derivative is the limit of a difference quotient. So let me kind of just talk about this. There's not really too much math to calculate. This is more just a concept discussion, right? So with a derivative, we can do lots with derivatives, but the main motivation for finding the derivative is to find the slope of the tangent line. That's the main motivation for it. Now we also know that this is velocity or instantaneous rate of change, and that kind of thing. All right, but to calculate a derivative from first principles, right, you do the limit as h approaches 0 of the what we call the difference quotient. So it's the difference of y values divided by the difference in x values, and of course in most textbooks they cancel out the x's and you just get h on the bottom. But it's the difference in the difference, y2 minus y1 over x2 minus x1, and we close up the bottom to get the bottom to approach 0. Remember, the bottom never equals 0, it approaches 0. If you divide by 0, you get something undefined. You're dividing by a positive quantity or even a negative quantity that's getting close to 0, and you're calculating a limit of this, right? All right. So what do? In essence, what we're doing is we're subtracting, and then we're dividing, and then we take the limit. This is the three things that you essentially, to break down into its basic parts, these are the three things that a derivative essentially is. Difference, quotient, and the limit of that, right? So we're going to enter into something called integral calculus now, and you'll be doing integrals for quite some time if you go on and take calculus 2, calculus 3, differential equations, or higher level maths that have to depend on integrals. Even some statistics classes depend on integrals, physics, those kinds of things. The main motivation for this is this question up here. How do we find the area bounded by the graph of a function in the x-axis on a closed interval? And I'm going to talk about that in more detail here in a moment. But that's the main motivation for integrals, is to find the area between a curve and the x-axis on a closed interval. Okay, so I'll leave that part out, but that's what you're finding, the area between somewhere and somewhere, right? And the symbol that this comes from, what we're going to be doing is taking the limit as something called delta x approaches 0, and for all intents and purposes, the delta x is a lot like h. It's a very small quantity between two x values, right? Kind of like this. But what we're going to do is we're going to take the limit, instead of subtracting and dividing, you're going to be multiplying first and then adding, and then take the limit. So let me explain what that is. You're going to find two things. You're going to find an x value, a delta x value, right? And you're going to find f of x something, some f of x within an interval. And I will explain more about this x subscript I next week. And we're multiplying these things, and then we're going to add them together with this summation. So it's the limit of a product sum instead of the limit of a difference quotient. So you multiply these two things, and you need to multiply two more things, and you need to multiply two more things. So this I will change. You'll have an x1, x2, x3, x4 all the way across the interval. You'll be multiplying them by these little changes in x. And then when you get done multiplying all those products, you will add them together, and then you take the limit of that sum. And that's essentially what we call the Riemann integral. There's a man whose name is very famous for integrals and some other things, but his name is Riemann, and we'll talk about him in the next video. Okay, so Riemann is sort of the father of integration, whereas Newton, Leibniz, those guys are pretty much the fathers of derivatives. Okay, and Lagrange goes in there too because of his notation. Okay, all right. So what about this area thing? Like, what am I talking about? Okay, and basically later we're going to call that limit an integral of something, but we'll talk more about integrals next week. So let's say that we have a graph. So here's your x-axis and y-axis, and we'll have a closed interval from, let's say, x equals a to x equals b. And I'm just going to draw the graph of a function. So I'll draw a nice concave down increasing function. Maybe it's a logarithm or something like that. Okay? And we're going to look on a closed interval from x equals a to x equals b. So these are two vertical lines, right? This is the line x equals a that goes through this part of the graph, and then the line x equals b is this vertical line, right? So now you have a picture of what the heck I'm talking about, right? What we're asking is how do we find this area in here, the area between these two vertical lines, so bounded on the left and right by the closed interval, but bounded above by the graph of a function, and bounded below by the x-axis. Now, if this function were a straight line, we could do this, right? We could divide it into little polygons. Maybe this thing turns out to be a triangle or a square or circle or something that we know how to find the area of from geometry, the simple shapes that we learned how to find areas of in geometry, right? Or some math class that taught you those concepts. In North Carolina, we don't have a geometry class anymore. We teach geometry in these other classes. Math 1, 2, 3, and 4. All right, so let's say that we're asked to find this area, right? Like, how do I do that? So one of the ways that that is thought of is by putting little rectangles here. So we'll have a rectangle here, and then we'll have another rectangle here, and then another rectangle here, and so on. And there's nothing saying right now that the rectangles even have to be the same width. You can see though that my rectangles aren't exactly getting the area, right? But if I add those rectangles together, and I meant for that last rectangle to coincide with x equals b there, sorry about that. But I start with x equals a, and then I kind of have to pick some number to add to a, right? And so we'll call this, x1. And we'll call this x2. And I hope you can see me writing really small. x3, x4, x5, x6. And then this would be the x7. So there's 1, 2, 3, 4, 5, 6, 7 rectangles, because there's, starting with x equals a, after that there's 7 numbers, right? Okay. So how would you find the areas of these 7 rectangles, right? Well, for each one, what you'd have to do is you'd have to take the width of the rectangle, which is the difference between x1 and a. So that would be the width across the bottom, and then, or the length across the bottom, and then the height of the rectangle. Well, the first one would be f of a, right? That height is whatever the y coordinate is at x equals a, right? In fact, let me label that on the graph. This point right here is the point a, f of a. You might remember that from when we did the slope of the secant line, or the mean value theorem, or those kinds of things. Okay, so that's just the area of the first rectangle, right? And then you'd see that there'd be more rectangles, right? The next one would be, the width of that one would be x2 minus x1. And then I'd have to take a different y value, and the y value here would be f of x1, and I'd use that as my height for the next rectangle, right? And then I'd have x3 minus x2, and hopefully you can see the pattern, right? So I'm just actually going to write all these out. And there's going to be 7 of them in total, as you can see, right? And the last one, the y value there is going to be whatever x6 is, its y value, right? So this would be b minus x6, so from here to here, times this height. And then I could add them all together, right? Add them all together. Okay, so this is called a lower sum. And the reason why it's called a lower sum is because it's an underestimate of the pink area, right? If I went and covered all these rectangles in, it's going to take me a while to cover all that, but you can see like we're leaving some of the area out, right? Oops. Yep, there I go again. I messed up. There we go. Hit my button I shouldn't have hit. But anyway, you get the idea, right? There's some area that I didn't account for that's curved up here. So a good question is, how can I improve my estimate? How can I make this a better sum? And the answer is to get more rectangles and to make them skinnier, to make them more thin, right? So if I had, 500 rectangles, they'd be very, very thin, and I'd have less leftover area, right? So what happens is that this width, this what I was calling earlier, this delta x, is what these things are, right? And then these are f of different x's, x subscript I. So I is 0, 1, 2, 3, 4, 5, and 6, and so forth, right? And again, this is a lower sum because it's an underestimate, right? It's an underestimate. Now, I can do an upper sum if I were to make my rectangles above, and hopefully you can see this yellow above the white there, right? So yeah, now I'm getting too much area. And in that case, what would happen is I would use the right side of each rectangle as the y value. So if this were x1 and x2 and x3 and x4, and that yellow doesn't really show up very well, and this were b here, the last y value would be f of b, right? Then that would be an upper sum. Okay, and later on next week we'll call these left-hand sums and right-hand sums depending on which side of the rectangle you use for the height. And you can even split the difference and you can find a midpoint sum, right? You can take the midpoint of the interval and use that as the height, and that way you can kind of have some over and some under. Even still, it's not going to be exact for all functions. Not for most functions, it's not going to be exact. But this is the way that you can find the area, okay? At least approximating. So this is all the approximate area. And later on, we'll take those rectangles and they'll be so skinny that they're going to look like line segments after a while, right? They look like line segments. And I didn't prepare this. I did not prepare for this, but I know that Shodor has an area tool. It's called integrate. Let's see if I can get to it. It says it's unsafe, but it is definitely not unsafe. Oh, it doesn't work anymore. Okay. Well, I'll see if I can get that up for you next week. There's a Desmos one that maybe, yeah, here we go. There's a thing on Desmos where you see the number of rectangles, and if you increase the number of rectangles, look what happens. The estimate gets a little bit better as you increase the number of rectangles. And if you only use, say, 1 or 2 rectangles, that's not a very good estimate, right? So this is an applet is something that used to happen when JavaScript was allowed to be used in web browsers, and now it's kind of obsolete for JavaScript. But anyway, you can see, I just wanted to visualize, or help you visualize what's going on, right? If there are only 7 rectangles, this is not the best area approximation, but if you get way, way more, then you're getting a better approximation, right? And you can see that as n approaches infinity, that the approximation starts to approach the actual value of the area without needing an approximation. So there is a limiting process involved, and we'll talk about that more next week. But anyway, I wanted to show that to you. And I just thought of it, to be honest. Okay, so this is kind of the beginning. I'm not going to work any problems right now. I just kind of wanted to sort of answer that question and whet your appetite, if you will, for this thing that we call an integral. So the integral of a function with respect to x, that's how we would say that, right? And this integral is a limit. of a product sum, right? So there's a product of two things, and we're taking the limit of the sum. So believe it or not, in Old English, this is the long letter S. It's called a long S in Old English. So that's what the integral really is. It's a long letter S, in case you were interested. So anyway, that's all for this week. My students are getting ready to take a test, so good luck on your test. And reach out if you want a copy of my book or if you need any help. I look forward to hearing from you.